everyone. My name is Alex Scott. I'm joined here by my co-host, Paul Bryant. We're going to be talking about Jacamar CI today, working through some examples with GitLab, really focused from the user, like the researcher perspective. So yesterday we gave a presentation that was more so on the system administrator, how to get Jacamar set up on your HPC cluster. Today, we'll instead be talking about the perspective of someone working on one of these projects that is hosted on GitLab. If you're here at the lab at Livermore, this would be the one probably best targeted to you since we already have Jacamar runners set up on a bunch of our HPC machines. And so this would be you as a simulation developer or you as a library developer coming in and using Jacamar to run regression tests, integration testing, unit testing across the HPC clusters environments. So without further ado, let's get started. Here I have just a little bit of an overview of what we're going to be talking about today. First of all, I'm going to give a little bit of a background on what GitLab runners are, how they integrate with Jacamar. This was largely covered in yesterday's session, and so if you want a longer discussion where we get into a lot of the nitty-gritty details, I believe yesterday's session was recorded, and so you should be able to go check out that when it's published later on. We'll then go ahead and kind of run through some of the basics of using Jacamar, and then start getting into more advanced topics, like how we can use, batch schedulers. So we're actually running on the compute nodes rather than login nodes. We're going to cover container runtimes and how you can use run mechanisms inside of Jacamar to launch your jobs inside of containers through something like Podman or Charlie Cloud. We're going to also talk about optimizing with large Git repositories and a few other kind of fun advanced features of using Jacamar in HPC environments. And many of those will be hands-on examples. So we're going to give you guys some accounts to a test GitLab instance, and we'll be live editing the files together and then submitting them and watch them run. We have a parallel cluster environment on AWS where those will go and be executed. So this is a little bit of the background of the GitLab runner. Again, we covered this in more detail yesterday, but to give a little bit of a background just so that folks know, a little bit of the lead up on what is Jacamar. We've got the GitLab server, which everyone here is probably familiar with. It's that web interface that you're used to using or, pushing and pulling code from via SSH or something similar. So that's this GitLab server up here at the top. The GitLab runner is a program that runs on, in our cases, lots of the login nodes for our HPC clusters. And this GitLab runner pulls the GitLab server, checking for and asking for kind of tasks that it can go off and execute on the behalf of users. The GitLab runner really came up inside of the cloud computing space. And so there's a lot of assumptions baked into that around running in, isolated virtual machine environments where you're not having multiple users on a single machine. So you're not a multi-tenant environment inside of your specific compute system, but really you're focusing on isolation through virtual machines. And so Jacamar, and I'll let Paul get to this in a little bit, but really morphs and allows us to run GitLab runners inside of HPC environments where we have many users using the same, bare metal machines. To talk about that a little bit, Jacamar is a custom executor for the GitLab runner. And so we didn't have to go and re-implement the whole GitLab runner from scratch. Instead, the GitLab runner provides these kind of pluggable interfaces. And so you all, if you've used GitLab in other contexts before, might be aware of either the Docker or one of the virtual machine executor types. And so these really allow us to use that base GitLab runner and then extend it with functionality from Jacamar through this custom executor type. And that allows us to natively integrate with GitLab. So your jobs show up directly in GitLab itself. You see all of the job logs as they flow in there. And as GitLab and the GitLab executor, or the GitLab runner, excuse me, update over time, we don't have to maintain as tight of a coupled functionality there. And we instead are this very nice plugin that allows the executor to run more natively in HPC environments. So without further ado, I'll hand it over to Paul to talk about what Jacamar CI is, and then talk through some of the architecture and get us started using it.
So as Alec mentioned, Jacamar CI is this driver for that GitLab custom executor type. And so as part of that, the GitLab custom executor will generate job context for Jacamar CI. This is like the environment variables. It'll also generate job scripts. And these scripts include things like how source code is cloned, how artifacts are managed, how the cache is managed. And Jacamar takes the responsibility for executing these on a local system, while at the same time enforcing a whole host of configurable rules that the admin of the runner wants to see. So that is kind of why Jacamar is split into these two separate applications, Jacamar Auth, which is that authorization focus layer, and Jacamar, which is the user scoped layer that, so with Jacamar Auth being enforcing, okay, who you are, what permissions you have on the machine, are you allowed to run on the machine, who you should run as, if you should run as yourself, or maybe a service or bot type account. And then Jacamar being that user scope that finally gathers all that context, the job script, all the environment variables, loads your local environment and actually runs the job. And that can run against things like just your local bash shell or an HPC scheduler like Flux or Slurm. The important thing to realize when it comes to like what Jacamar is aiming to do is the same environment you see when you log into the machine is the same environment Jacamar wants to provide you for running your job script every time. And so it's going to create a clean bash non-interactive login shell, for example, in the shell environment, and then run the GitLab generated job script there. So you should, whatever behavior you're seeing when you're on the login node, for instance, and you're running make build, you're going to get the same behavior when you run make build in a script, in a GitLab CI script running through Jacamar. And so this kind of brings us into two additional concepts within Jacamar's configuration that I wanted to highlight that I think really apply to today's tutorial. One is executors. Alec talked about executors in the GitLab sense. Jacamar implements the same thing. And the idea is pretty much equivalent, where it is how Jacamar is going to run the job script. In our case, in the demo environment you're going to use, you'll have access to a Slurm and shell executor, where in the case of the Slurm executor, for instance, it will every CI job it runs, it will equate to a single job submission to Slurm. There's an exception to that we'll go through in the tutorial called scheduler actions. That is exciting. That gives you a little more flexibility. But for the most part, it is kind of a one-to-one relationship. And then the run mechanism, which is kind of this how we run the bash script within the executor. Traditionally, that is just bash. That is just your shell. However, because, well, one important note before I get to that, the GitLab runner will always generate their shells in generate bash scripts. There is no other option there. So you have to be okay with the GitLab generated job scripts being bash. Now, within that script, if you want to run some other shell script that you have, that's okay, but the initial script you write in the CI YAML file will always be bash. And then the run mechanisms, how we realize that, those are things like HPC container runtimes like Charlie Cloud, Podman, or Apptainer. The asterisk with Apptainer is it's not as fully supported as Charlie Cloud and Podman, and probably needs a little bit more feedback from users to get there. So that's kind of like, and then basically Jacamar is going to generate this sort of command or interface to the underlying scheduler that, if we look at CLI, would look something like this, where it would be the scheduler, in this case a Flux runtime, but Flux chrun is the run command for Charlie Cloud, if we're using that run mechanism, and then the actual script that that the runner generated for in this case, that would step script would be the combination of your before script and script in your CI YAML file. So those are the high level things from Jacamar you probably need to know to get started, and we'll cover more of it, and you'll actually get hands-on during the tutorial. So Alex is going to talk a little bit about spec build farms.
Thanks, Paul. Yeah, so one of the workflows that I wanted to highlight here that is often used at Livermore using Jacamar is that we build a lot of like SPAC CI/CD build farms out of Jacamar. And so what I mean by this is um, Jacamar allowing us to run on HPC environments, typically with a runner, if you have a single runner that's maybe not using Jacamar, you have a dedicated CI node that's just set up and it's just processing something like a SPAC build. Here, each of these colored squares are each they're each a application build inside of SPAC, so something doing a compile. And you can kind of imagine that this is an amount of resources that's used over some period of time. And so really like the area under the curve, the integral is the amount of compute space that we're using here. So typically, if you just have a single node and you're doing a SPAC install, all of these builds have to happen sequentially because you're kind of building up a dependency tree. So you can start with low level stuff, building up from your libc. You might have zlib, you might have some intermediate libraries. You might be building an MPI installation on top of that. And then you get to your top level simulation code. Well, that takes a long time. And so Jacamar executing on the HPC environments really gives us the benefit that when we're using something like Paul was just talking about with like the Slurm executor, we're submitting these jobs off to batch nodes. And so each of our CI jobs, we can encode the dependency information there so that they execute in the correct order, but we can farm those out across our whole compute cluster to get our builds or our multi-stage compiles done much faster. Here you can see we're running over 3 nodes, and because we're able to distribute this work in parallel, we're able to get this work done a lot faster. So what does this actually look like? Well, here's a quick screenshot from some of the SPAC build forms that we have here at the lab. You can see we have a whole bunch of projects or a whole bunch of applications that depend on gmake. This makes a lot of sense. Lots of things use make in their build. But then building up from that, you can see how much parallelism we're able to gain by spawning off all of these jobs as their own separate CI/CD executions and then submitting them over to, I guess, batch nodes, throughout the compute cluster. So all of these could be running on separate nodes, or they could be packing, using part of a node onto just a couple of nodes. But anyway, and then there's on and on more off to the right of this. But this is really just to say that Jacamar allowing you to run on true compute resources allows you to scale, whether it's your unit testing or regression testing or building of SPAC environments out so you're able to operate much faster. So now we're going to go ahead and we're going to get started doing some of the hands-on exercises today. So head over to the link bit.ly jacamar-tutorial-accounts. There you'll be directed to, and thanks Paul for posting that in the chat, you'll be directed to a Google Sheet. On the attendee side of things, feel free to just put your name down, and then your username and password are for the GitLab instance. There's a couple of directions there on the sheet, but it'll tell you you can go to tutorial.gitlab.jacamar.org or jacamar-ci.org. There you'll go log into GitLab, and then once everyone is set up and logged into GitLab, we'll go ahead and start creating our first repositories, set up some CI/CD scripts inside of that, and I'll hand it back off to Paul to kind of walk us through the getting started with Jacamar. Also, if you have any trouble getting into GitLab, signing up on the Google Sheet, any of that, let me know. I'm happy to help folks out, and I'll be lurking around in the chat.
A couple notes. This is fairly self-guided. You can go through most of it. There's a couple of features that are not enabled today, and we've put notes where that is the case. However, you do need a GitLab instance set up to run it, and we kind of don't have a way for you to do that on your own at the moment. However, the skills you kind of learn here, or the ideas you might get for your project, will equate to any GitLab instance. Nothing you can nothing is special in terms of this instance, in terms of like you can't realize on any other GitLab instance you have, even regardless of subscription level. So if you're running on a free tier GitLab instance, you can still use runners, you can still use CI in the same way that if your institution is paid for. If you're not familiar with CI/CD at all, I've added some links to some resources from I believe from GitLab and the Better Scientific Software efforts that might be worth going through. If if you find those, if you need more information on some of the basics.
For getting started with this repo, I'm just going to point out that to go create a fork of this repository, when you first sign in to the GitLab, you'll be presented with kind of like your work and projects, and it'll say you haven't contributed any projects yet. Up there at the top, there's a member tab. If you click on that, everyone is a member of the tutorial group. And from there, you can get to the Hello Numerical World repository. I can also copy and paste a link of that in here, and everyone should be able to access that. But then you can go ahead and create a fork based off of that as we start working through some of these examples.
When you get on, start by just creating the fork of the project. There's more information in the README about the original purpose of the Hello Numerical World project and links to the actual training materials. We're using it as an easy thing to build and generate artifacts with. We're not going to go through the actual science or lessons from that tutorial here, but I encourage you, if you're interested, to go visit some of the work Mark Miller did in this space. So to get started, once you fork the repository, we're gonna start by just taking a look at the available CI/CD resources associated with that project. So under this project settings, CI/CD, you should see a whole bunch of information about your project's access to CI/CD resources and the configuration of it. Under general pipelines, there's a couple things I wanted to highlight. One is the CI/CD configuration path. The file you're targeting by default is the .gitlab CI YAML file, and this defines what the pipeline looks like and what GitLab is going to realize. This doesn't have to be the file. It doesn't have to be on your root path. You can change it, but you can also reference other projects for your CI/CD. So for instance, you could manage your pipeline in a whole nother GitLab project. All that matters is that the user who triggers the pipeline has access to that project as well. I've seen some larger projects do that. You have some flexibility in how you want to organize there, but ultimately it is YAML, so you are still confined to the restrictions of YAML. There's some other options about Git strategy here you can set. Alec is going to talk about those later, and some of the flexibility you have and why you might choose different strategies. And then finally, the timeout. This is the default timeout for all jobs in your project that you run. You can set them lower at the job level, but ultimately the wall for that, or the ceiling, is going to be this. But actually, there's one more restriction, which is the runner set timeouts. Where you want to set larger timeouts is cases where you know your jobs are going to run for a long time, or in the case of the batch executor, where the job is going to sit in queue for a long period of time. Unfortunately, currently, the time in queue also counts to this timeout. So in the case of a batch executor, you don't want to rely on the GitLab runner generated timeout for how long your job is going to run. You're instead going to want to rely on setting like a wall clock on your like sbatch or flux run or PBS, which would be bsub, or commands. Everything else here are things that I encourage you, if you start using a lot of GitLab CI YAML file or GitLab CI, to kind of dig through. Let's see. The other configuration option I wanted to highlight here is actually how you identify the runners that are available to your project. Again, in the CI/CD settings, if we look at runners, we can see what runners are available, and the tags. Tags are how we identify and target runners, And so it works on what runner is available first to take your job that meets whatever tags you define. So if I'd only define the tag Jacamar, it could use either the Slurm runner or the shell runner. But if I define Slurm or shell, it's only going to use one of these runners. Runners are also split into like the idea of instance runners available to everyone on the GitLab project, GitLab instance self, and group runners and project runners, which are scoped accordingly. And may be helpful in cases where your project has very specific test resources that are not available to everyone on the instance. You can still use those runners as part of your entire pipeline by registering them at the group level or project level and assigning appropriate tags. So to get started here with the tutorial, what we're going to do, open this in a new tab really quick so I can get back to it later. All right, so we're going to go to edit, and we're going to use the web IDE GitLab provides. This will look very familiar because it's just VS Code. There is a lot, I'll note there's a lot of work going into this space with the web IDE. So if this is something, there's no extensions that turned on our end at the moment, but I know there's a lot of upstream work in this space to make it a more similar experience to local. So what we're going to start with is we're going to start with modifying the GitLab CI YAML file that exists currently. I just created a small placeholder file. And we're going to start with a very simple job, and we're going to walk through kind of what you're setting up here. So first off, default is a keyword in CI, in the CI YAML file. And it defines, oh, okay, I'll slow down a little bit. Before we kind of dive into the Hello Container one, I've tried to link everywhere where a keyword is being used to the upstream documentation that gives you more information. If you ever have a question, that's the best place to go look is GitLab's official documentation. Your local GitLab instance also has docs, and it just mirrors what's upstream, the upstream docs looks like, but they're pinned at the version of your GitLab. So if you're running an instance that's a bit behind of the latest release, that may be the safer place to look for documentation on what does default do and what do tags do and ID tokens and things of that nature. The other note I put here is we're going to show off using container runtimes by targeting specific images, like container images we've pre-built. That is not required. That is completely optional, and it's just to show off another feature. I know a lot of people probably will just be using traditional like login like environments or batch environments. In those cases where we would do something like use a GCC container to build, you would do instead add into your script like module load GCC or whatever compiler you might have locally available to you. All right. Hopefully that's everyone's got the fork and are in the web IDE now. I'm gonna move on. So in this case, we're just going to copy this code block is YAML into our GitLab CI YAML file. And the default is a predefined variable, sorry, not predefined variable, but a feature within GitLab CI YAML that is going to apply these to every single job in the pipeline. However, if you put tags at a job level, it will override what's defined in the default level. So tags are by default, we are going to target the Jacamar and shell runner. So we're going to exclusively target our shell executor by default. We're also going to do something called ID tokens. This is a relatively new, probably came out a year ago feature in GitLab. It used to be a default behavior, but now you have to explicitly say when you want a job level jot created and injected into your CI job environment variables. Jacamar requires this in order to handle authorization. So this jot is created by the GitLab server and signed by it, and Jacamar can validate it. if you don't have this, Jacamar is going to very explicitly tell you what to include in your job to work. So it's very, if you do run into it, it's very easy to fix, and it's very explicit in how to fix it. But we're going to include this and an audience that matches our GitLab server. Interruptible is helpful as well. That means that there's a variety of cases where GitLab will stop a running job. You might want to leverage this. By default, it's not on because there's actually cases where you might really not, you really would not want GitLab stopping something that is running when something new comes in. But it is helpful, especially if you're doing a lot of development and you're trying to save resources. So if you have a batch job being submitted and running on compute and you have interruptible on and something comes along that and a new commit on that branch would make that irrelevant, the runner will get a signal to cancel the job. It will then send the signal to Jacamar, and Jacamar will run something like scancel or flex delete. So this we're going to run a very simple script that just tells us who we are and looks at the local environment. We're just going to commit it to main to save time. And then after you've committed it, if you go back to your GitLab project in the sidebar and look at the builds and the pipelines, you should see that it ran hopefully correctly. And you'll actually see that some details about this might be helpful is you'll see the version of the runner, you'll see the version of Jacamar, you'll get some information about Jacamar as well. It'll provide you some details on what it's running under executor rise, some functionality available to it that you might not be aware of that's configured on the Jacamar side, who it's running as, and you'll notice that it's running as my user. In your case, it's going to be demo and whatever number it is, and it's going to be running in this just Ubuntu login environment. So we're going to do the same sort of thing, but this time for a container through that run mechanisms. Simply providing an image is an indication to Jacamar that it should run your job in a container using the defined run mechanism. In this case, only Podman is enabled on this environment. So apologies to Charlie Cloud Container users on this call. Normally, it can be configured for just one run mechanism if that's all that's supported on the machine, or multiples. And I provide some examples here to how to target different run mechanisms with CI/CD environment variables. And before I submit this, let's go ahead and submit it. And what we'll notice when it runs okay. We'll notice that the container running as root because it believes I'm root in the container. But I'm not. I'm actually still downscoped to my user, and I'm running on this Alma Linux environment. The thing about run mechanisms is you'll still always downscope to your local user before running anything, before running these like Podman or Charlie Cloud or Apptainer environments. The one thing about Podman I'll note is it gets tricky with sub-UID, sub-GIDs, because we have to mount in files that your user owns into those spaces, and Jacamar is very strict by default, preventing, for instance, like it's going to put your files in a folder that you own and only your UID and GID owns, so you don't accidentally end up sharing tokens that get created during CI jobs. So that we don't cover that here, but if you are doing stuff with sub-UID, sub-GID, that might not be as easy to realize in Jacamar with some of the default mountings that have to occur. Finally is batch support. In this case, we have, in this case, we have another simple hello job that will target our Slurm executor. So we're overriding the default tags in this case. We are defining variables, in this case, scheduler parameters. These will be injected into our command we're sending to Slurm, along with default behaviors Jacamar controls, such as like the output for the job. In the case of Slurm, we have to pipe output to an expected location. And we put some controls over job names so we can find the job later. But this is fairly simple, that we're going to run a very basic command that shows us that we're running on the compute node for our script. However, the important note here is after script does not run on compute. So I mentioned before, well, let me add this really quick. In the case of job submission, or in the case of, I guess, the runner-generated job scripts, before script and script are both combined into a single bash script that the custom executor gets to run. And we don't have any concept of where the before script starts and where it ends. So we just have one script that we submit to the batch executor. However, host after script is different. And this is like, this might throw you for a loop sometimes. So be careful when you're setting this up. AfterScript is substantially different both in how the batch executor treats it and how GitLab expects it to behave. The batch executor doesn't submit the AfterScript to the compute node. It runs on the login environment, which is helpful because you can maybe perform some actions there that you can't perform on compute after your job is done. However, the AfterScript is limited substantially in the amount of time it will run. GitLab limits the AfterScript, I believe, to 5 minutes. Then it will time it out. So regardless of where it's running, and regardless if it's shell or batch or Docker or whatever upstream executor you're using, the AfterScript does have like a time limit that is different from your entire like job timeout you might have defined earlier. So that's just be aware of that. So don't try to shove too much in your after script. And if you need to run a lot after your job of like post-processing or it's like some sort of cleanup, or maybe you're uploading artifacts of your build to another location, you might need to split that out into another job in your pipeline that comes in a separate stage. So that's running now. We're still
There's like
running
a
two jobs. Oh, yes.
question asked. Is it possible to override the time limit for the after script step?
No, I
Yeah.
believe that's hard coded in the runner itself. So we can't change that.
Okay. Yeah. And then your suggestion then would just be you can create another job, kind of like an ending job in your tutorial pipeline or in your CI/CD pipeline, and you can set any timeout really for that specific job if you have something that's taking a longer amount of time to clean up. There's some rules. We'll show an example later on, basically, to make sure that that job always runs no matter if the jobs that came before it were successful or failed.
Yep. Thanks. So this is the job results. So like I mentioned, this runs on our compute resource. This runs on our login node because that's our after script. And the job is completed successfully. Jacamar checks the state of the job upon completion and reacts accordingly that if it wasn't completed and it will fail this job. So anything but an exit status of 0 in shell and slurm in any executor will result in a job failure. All right. So there's one more thing I want to cover in this section, and I'll pause for some more questions. There's something called the pipeline editor in GitLab, and I think this is a really helpful tool. If you're working on a pipeline, you can pick your branch, but it comes with the linting and the visualization already kind of built in. So if I make a mistake, it's very clear on what's happening, where it took place. It'll tell me. Obviously, it won't tell me if my scripts are incorrect, but it will at least check my YAML and it will check to make sure the keywords I'm using are accurate and are supported by GitLab. It provides a really helpful feature in visualizing your pipeline. Not particularly exciting at the moment, but referencing back to the pipeline Alex showed, where it is very complicated and there's lots of dependencies, and it is can be very valuable. There's a new validate feature, but the other one is the full configuration, and this is helpful later if you get into the idea of extending and including bits of your CI YAML file. And this is functionality we kind of touch upon later, where you can reference jobs or components managed in other repositories. So I personally use this to manage core CI functionality for a number of our projects at Oak Ridge in one repository, and then we basically reference that. And full configuration will realize that entire YAML file for you to see. So if you're following along with the tutorial, hopefully it all works and you don't need to use this. But if you're working on your own, you're trying things, I recommend uh, utilizing this, if not to write the YAML, just to verify it's actually functional. And it does have access to other files in your repo. So. All right. So that kind of wraps up like the initial uh, basic tutorial, kind of the hello environment. So I want to stop here and see if there's any questions. Hopefully I didn't miss anything with what we covered. And if you're working ahead, also great. You're going to start entering the SPAC CI section, and I want to hand that over to Alec since he is the expert.
We're going to head back over from where we were running our demo jobs inside of our Hello Numerical World. We're going to, again, go open up that web IDE. I've got it here in another tab. So if you still have it open from the previous section, feel free to just jump back in here. And I'm going to select everything inside of our .gitlab YAML CI script and delete it. And we're just going to start over building up our SPAC CI section instead. So I'm gonna, again, paste kind of the default start that we had from before, setting up these defaults, the CI, basically the job tokens that we were talking about before. And then we've got two new parts here. Stages inside of your GitLab YAML files are, you can think of breaking your job into distinct parts. So this might be like build, testing, and releasing something. Or in this case, we're gonna have two stages, generate and build. Generate is we're going to do our SPAC concretization. And so that really means we're going to figure out all of our dependencies. We're going to create a build plan. And then in the actual build stage, we're going to go off and compile each of those components up into a software stack. So we'll have our two, and I'm just going to copy out this for the generate stage. Oh, that's not. There we go. So this is what I was just talking about for that generate stage. This is going to go and do our SPAC concretization. If you haven't used SPAC before, no worries. It's really just saying SPAC has a process where we're using the logic solver to figure out all of the valid dependency versions that we can use to build up a dependency tree. And that's the process that we're going to go execute here. We're going to use this image tag. Paul talked about this a little bit before, but we're going to end up using the podman run mechanism here. And it's going to pull basically the container that we've prepared for this tutorial, just so that it has a bunch of the dependencies already set up and configured for us in a reproducible manner. But you could just go execute this directly on your HPC cluster and not need the container. And then we're also just specifying a custom entry point here for our container, which is loading up a bash shell that will go and get started. The next stage that we're gonna, or the next part of this that we're gonna talk about is setting up a persistent volume. And so here, jump back out to the variable section. So Jacamar, when you're using something like the podman run mechanism, gives you these variables, Jacamar volume, and this can be essentially any number starting at 0 and working your way up if you need multiple bind mounts into the container. But this allows us to create a persistent mount on our shared file system on the HPC cluster outside of our container, bind mount that location into the container. So here we've got, let me close this so we can see a bit more of this. Um, Conveniently, we're mapping kind of the same path, but this would be the path outside the container. It's separated by a colon. And then we've got the path inside of the container that we're going to be going and running under. Um, so we'll set up this persistent volume claim. This allows us just to share the compiled artifacts from SPAC between the different jobs as they're running through the workflow. And lastly, we're going to say um, what we actually want to run inside of this. So here, we'll define a script. We're going to source the SPAC setup. We're going to create this kind of build cache so that we can push out these built artifacts outside, push them basically through the file system outside of our container, save them on the hosts so we can reuse them across different jobs. We'll then go ahead and activate our SPAC environment, which is kind of the list of all of our dependencies. SPAC CI generate takes this build plan, basically all of our dependencies for a specific software stack, and it outputs them as a format that GitLab itself can use. And so here we use some functionality that's called a dynamic child pipeline inside of GitLab. And so SPAC is computing essentially all of the CI jobs that we need to do. And then we're passing off that build plan to GitLab. And then natively in the GitLab interface, this is what I was showing a little bit earlier in the presentation, GitLab is going to go run all of these SPAC builds in parallel across a compute cluster. And so we're taking, we can dynamically generate this any way we want, and it's really a powerful functionality inside of GitLab. We can have SPAC go and inspect our environment, figure out what needs to be built on the fly, create that, you could kind of think of it as like a dynamic set of jobs that need to be executed. It's going to pass that. Basically, it creates this as this pipeline.yaml file. And that gets outputted as an artifact from this generate pipeline. That artifact is ingested by GitLab and then used by GitLab to create the child pipeline of all of these dynamic jobs that will go off and execute. Um, the last little bit that we're going to add into here is for our build jobs. So these are going to be all of the jobs that actually go and execute some of the builds for SPAC, compiling each little piece of software up from source. Or in this case, because a lot of those are already in the container, it's just going to pull them from the existing binary cache and install them. So we'll go ahead and save this as our GitLab.yaml file. There's one other file that we're going to edit here in here, and it's this spec.yaml. The spec.yaml is specific to the SPAC program. If folks have used SPAC before, you'll be very familiar with this, but it allows you to define a SPAC environment and a lot of the settings that would go into that. So we'll go ahead here and copy this full SPAC environment. We're going to replace it with our placeholder SPAC environment here. And we're also going to note that here we want to go in and add in our username. So under the build cache destination, the URL here is that bind mounted location that we used earlier. And so this is going to be our GitLab username. So in my case, I'm using demo25. So I'll just put in demo25 there. And then this is saying, what we're going to use from our container, as I was talking about before. These are the packages that we're going to go and install. So in our case, it's pretty simple. We're just installing readline. But it shows a bit of a complex, you've got a dependency tree with gmake and a few other things in here. And then this is going to be what's executed inside of those basically any of our jobs inside of here is a template that this will get filled out with. I'm happy to answer more questions on the SPAC YAML here, but it's a bit more SPAC centric than what we really need to know here. Um, for the purposes of this tutorial, we're really just saying this is a complex use case of CI/CD systems using dynamic child pipelines. If you feel like this fits into your workflow really well, or you need to build a SPAC environment, feel free to go look up dynamic child pipelines a little bit more, or the SPAC CI documentation. Um, but with all of that filled out, we will go ahead and push this up. So I'm just going to title it SPAC CI, do a commit and push, and then we've pushed up to the main repository. We'll see that this has kicked off our pipeline, and you'll see that we've got these two stages here, the generate and the build stage. The generate is going to go ahead and you can see that it is sourcing that SPAC script. We'll see that we pulled the container here. We've got kind of a local cache of a lot of these containers. So the pulls happen very quickly, but we pulled and set up our container. We prepared the environment. Jacamar is doing all of this for you. And so really your script is just waking up inside of the job. So there we go. We see it ran through everything. It said, these are the 4 different packages that I need to go build. And so if we go back here and reload this, you can see now we have some build jobs. And if we click into this, we'll get this additional child pipeline view. And you can see here, oh, I went back too far. We've got our GCC runtime that got built up. We're now building gmake. From there, we'll build package config, incurses, readline, and we'll be done. This is a largely, kind of one package build after another. But if you get into complex dependencies like I was showing earlier on, this can quickly fan out into you doing 10 or 20 consecutive builds. So we'll see we've made it through gmake, made it through package config, starting on our incurses build. And if we want to, we can click into any of these. We'll see that it grabs the container um, and it initializes the repository. And then inside of here, it's probably just going and grabbing the binary that we've already prepared, installing that, saving it out to the file system. So I'll pause here for a quick minute. In case anybody has questions, feel free to ask them in chat. I think I saw Paul's already answering some stuff, but if we want to bring up anything, we're welcome to here. Here's an example. If you have SPAC installed, if you've ever used SPAC before, you might be familiar with this command, but SPAC graph is essentially showing us the same dependency tree that we were seeing before, where you have all of these things depend on or rather, package config and incurses and readline depend on GNU config. Readline depends on gmake, and so that's getting installed out here. Let's see. Okay, we ran through that one. And we're off to our last build for incurses here. Or incurses and then readline as our last one here. So while that's going off and building, I'll talk a little bit about some of these rules here. So in the case that you're doing something like a complex, either a SPAC build or a complex pipeline, you might want to limit when that pipeline executes. So by default, when someone pushes something up to a branch, you're going to go run your GitLab CI on it. If someone opens a merge request, it's going to run CI on that. You can say, instead of always running on everything, I want to run if the commit branch happens to be the default branch. So in this case would be, if we're pushing to something like main only, if we're creating other branches, we don't want to go regenerate our whole SPAC environment. We only want to regenerate our SPAC environment when we push to main or master, one of these kind of your default and your primary branch inside of Git. And furthermore, we don't need to go rerun this whole SPAC environment build if the SPAC environment itself doesn't change. So we can further downscope and limit this to say only when we change the SPAC.yaml file should we actually go and then rerun. So while we are finishing our last incursors and then readline build here, I'm going to jump back into the IDE real quickly, go back to our GitLab CI YAML file, and I'm going to add in these two additional sections. First, right up here at the top, we're going to define what I was just talking about. And the significance here a little bit is the dot specifies, kind of like a dot specifies a hidden file in the Unix world. A dot here specifies like a job or a piece of config that isn't going to be executed by default, but we're going to use the extends directive, both in generate pipeline and in build jobs, to add in this rule so that we don't have to duplicate it in both places. This is really just a pointer. We're going to say, hey, both of these extend this hidden rule. So here, I'll go ahead and copy that extend CI rule. And we'll go ahead and just add it here right after images. Be careful to fix the indentation. And I'll add it here under the build as well. And so after this build finishes here, we could go push up this. And you'll see just because we've only modified our GitLab CI YAML and not the SPAC, then hopefully neither of these jobs will run. Once we are done doing these builds, I'll hand it back over to Paul, who's going to talk about project integration and just a lot of the really cool things you can do inside of GitLab CI, utilizing, kind of the stuff from Jacamar. Okay, cool. So we got our incursus, we got our readline build. I'm going to go ahead and commit our additions for the rules. And I'm just going to say I added the rules to limit the builds. We'll commit and push that. And now if we go back to our hello numerical world, we'll see that we added these rules and we pushed it. And there are basically that didn't kick off. There's no pipelines running now because we didn't modify the spec.yaml file. So that's a little bit of an example of how you can more intelligently limit when you're actually having to go do some of this work. So I use this really often for Git repositories that maybe you have a set of documentation and you have a project in. If you don't modify the project, you don't really need to go run your unit tests and integration tests if you're just, say, modifying the README or some of the documentation in the project. Vice versa, maybe you do want to test building the documentation, but you don't want to do that when you've only modified one of your C++ files. So with that, I'll hand it back over to Paul to talk about project integration and using Jacamar in some more sophisticated ways.
Thanks, Alec. One note I should have included in the docs about changes is it is limited to the default branch and MRs. Changes won't be properly enforced by GitLab outside of those two scenarios. So if you're using changes, you want to associate those rules with things like the default branch or a merge request for it to function correctly. All right. So for project integration, we're actually going to we're going to use the tools we built. Well, part of it we're going to use the read line. The rest of it's already kind of been built in the containers we're using to actually build, run, and plot some basic outputs regarding our Hello Numerical World application. So we're going to start by expanding the number of stages available and that will run in our pipeline to include run and plot. So to start with, we're going to first add a new job to our build to handle the GCC build of our application. So in this case, fairly straightforward, just we're going to make the application. We're also going to run a check during that. And as part of that, we're going to generate some code coverage, and we're going to examine that code coverage to help gather details for our job and also gather a coverage value. Most of the time, you'd probably split these out over 2 separate jobs where you're building something, then you're running your tests. This is just all clumped together in this example. And as I mentioned earlier, if you don't want to use a container, you might do something like module load GCC. That will not work in the demo environment. Instead, GCC is just available, or any module you wish to load. Finally, in this space, on the GCC build, we're going to want to capture some artifacts as part of this. So we're going to capture 2 things. We're going to capture the application we build, this heat application, which is and paths is relative off the CI project directory. So that root of your project, we're just going to build this heat application there. So we're going to capture that as an artifact, and we're going to expire it in 1 hour. The size and expiration of artifacts is something the GitLab server admin will set by default. So be aware that usually artifact size can be very restrictive. And so if it is too limiting, those are things like caching or using your local storage if you have other network file systems on those resources that you can store resulting artifacts that are greater than the size that you're allowed, and then just access them later. We have some notes on that, and those are just things you would have to script around, or if you use GitLab caching. And then we're also going to gather something called reports, which is a feature the server realizes for actually visualizing coverage reports. You're not going to see the visualization in this example unless you start making changes to the code, but I have included an image here of what it looks like. And I think it's helpful, especially for code reviews. And if you're expecting code to have some tests associated with it, it just provides visual clarity to that. The documentation up on the GitLab side explains what those code coverage reports supported are and provides some example applications that you can associate it with your project. This is just written for C, but you might have something in another language and you'll have to generate code coverage reports through those mechanisms. Finally, we're going to use some regex and actually identify the specific value of code coverage as like a numerical value. And again, this is presented back to GitLab and something you can see in the MR, but also if you're expecting to hit specific values, it's something you can utilize in like a badge on your project. So we have this, we're building the application. We want to keep expanding our number of jobs. We want to actually now run it. So we're going to add another job in. A lot of this starting to look probably fairly familiar to everyone. We're going to run this one on the Slurm executor. We're going to pass some new file scheduler parameters. We're going to run the application. It's just running dash-help to show it. And then we're going to run it here on this compute resource. And what we're going to do here is we're going to show off caching, which is the test results from this heat run is going to create a folder called test, and we're going to push the results of that to this cache. With Jacamar, we don't support anything but local caching. So this would be in your .jacamar CI folder. There'll be a cache directory, and the files will be stored there. And then it's the same in GitLab. When they generate subsequent job scripts, we'll retrieve the caches from there. And finally, we're also going to gather an artifact of the same thing just so you can visualize it. Artifacts, important note about artifacts, by default, subsequent stages will download any artifact they encounter. So the artifacts from the generate pipeline will be technically downloaded here, and heat run will will download the generated artifacts from both generate pipeline and the GCC build. And I'm going to show you how to override that behavior, I think, next. Oh, and we're going to run a test plot as well. Maybe I don't show you how to override that behavior. Well, that was a mistake. I should have. I guess what we can do here is I'll show you right now. There's two ways to override default behaviors when it comes to artifacts. One is dependencies, and then you can list out what prior jobs you expect dependencies of. This will only for example, would only download artifacts from build jobs, which they don't exist, but if they did, they would. The other option, and if you include an empty dependency list in your YAML, then no dependencies will be downloaded. This is helpful if you're generating a lot of artifacts and you want to skip that stage and avoid downloading and wasting time in those spaces. The other option is something called needs, and this is leveraged by the generated pipeline in the SPAC CI to create a DAG between jobs. So GCC build would start as soon as build jobs finishes. Well, not in this case because that would be a bad example. We could do something like this actually. And it would run immediately after generate pipelines finishes. So we're not going to use those here, but they're really helpful the more complicated pipelines you're generating and the more you're doing with artifacts and caching, or you want to start running jobs as soon as from one stage as soon as something in a prior stage is finished. So finally, we're gonna run. Oops. Oh, parallel jobs. I'll let Alec talk about that because he had some notes about it. But we can choose to add sort of parallel job in here. This is very straightforward and easy, this example, because it only has one job. But if you wanted to add additional conditions in here, it would basically rerun this command. Each one of the parallel jobs would run as its own CI/CD job. That it would receive this separate condition variable that you might list in this array. So I think we've got everything in here to run this pipeline. We're going to commit it, and we're going to take a look at where it's running. So because of the rules that Alec added, you'll see that we're not generating the pipeline, we're not building readline again, we've already done that, so we don't have to worry about it. So in this case, what we're going to do is we're just going to run our build. And then I broke Jacamar. Okay. I apologize. I thought I had that fixed. Okay. So we broke the coverage, so we're not getting that, but this is a good example case to highlight something else. After scripts, if they fail, do not fail the rest of the job. So don't do something in after script you expect to succeed and that hinge on the rest of the pipeline running. So I guess this did happy accident in terms of highlighting a feature that if you expect something to succeed, make sure not to run it in after script. It's only meant for cleanup, or in this case, gather and coverage reports, which isn't crucial for the rest of the pipeline to succeed. Finally, we're going to run it. You'll notice that if this was multiple things in our parallel job are running, we would have them all to choose from here. In our heat run, it's fairly straightforward. We've submitted this to Slurm. We've run it. Those artifacts have been generated, and we've captured them and uploaded them. And I'm going to make the screen bigger here. Artifacts are very helpful and easy to realize in GitLab. They provide a GUI mechanism for you to see if there's an artifact available. You can browse what artifacts you've uploaded. In this case, we've just uploaded the test artifact here. The results from that, And we don't have the PNG for that. But instead, what we would have to do to get the PNG is we'd have to go back here. Did we run the test plot? I didn't add the test plot, sorry. I was going off script, and then I skipped a crucial step. So hopefully everyone else followed along better than I did. Um, we added a test plot, and this test plot is actually going to use the results of the heat run in order to generate a PNG. In this case, we're just going to use GNU plot to run this. There's a couple other options available, but this proved to be the fastest for the tutorial. And so now if we run that, we'll rerun the pipeline again, and we'll get a slightly different pipeline. There we go. We'll run the heat run again, and then we'll run the test plot. And then that in the artifacts will just have a very simple PNG file that'll get uploaded. Again, it is something that we upload. We can choose to expire it whenever. Subsequent jobs can receive it. Artifacts by default within GitLab and CI/CD in general are limited to project, like developers on the project. However, just about anything in the GitLab project can be changed configuration wise, like in terms of what permissions others have. If you have a particularly open project or maybe on an open GitLab instance, you might be able to make that those CI/CD results and the artifacts available to anyone looking at it, and anyone can download them. You might not want those behaviors. Those are things all found within your project your project settings. It's one too many. There you go. Under the settings for your project, and those are things I encourage you to explore depending on your project specific requirements. So yeah, we can just click download and download the artifacts. We're going to trust this to run correct and download the PNG, and it'll be zipped up and available for you to view locally. The browser does not. The browser really is just there to browse the file system and download specific files, browse the directory structure, not really for you to view the files in your browser necessarily. Most of them aren't going to open. So, okay. Before I hand it back over to Alex to talk a little bit about parallel jobs and some of his recommendations there and scheduler actions, I wanted to touch upon a couple of the additional jobs that are not going enabled in this tutorial GitLab instance, but I think are really exciting workflow additions for anyone who might already have a CI/CD YAML set up for their project or is getting started with it. One is releasing your application. The GitLab CI job token has some flexibility in what it allows you to do to your own project, not to other projects necessarily, but to your own. And one is actually tying it to a release job in your pipeline. So this example kind of highlights how we can upload that heat binary we built in that build stage, and we can upload it using the CI/CD job token to our GitLab project's package registry. And it's kind of a generic package registry. There's a couple other options there, like Python and RPM. I think it's RPMs or Debian packages. There's some options available that GitLab provides you. You can explore. But generic is just as simple as we want to upload this file to GitLab, and GitLab will serve it up to other users. And we're going to kind of run this as kind of a release stage that also doubles as a way to release a new version. So for instance, this we're tying to rules again, but we're tying it to a very specific commit tag, the number 0.0.1, for instance. This would generate a GitLab CI/CD release with this name for targeting the tag we've just created, with a description, which is not original, but can be whatever you want, and links to different assets. For instance, what we uploaded to the CI package registry. We're using, whoops, sorry. We're using a specific image here, the the helper image. I've provided a reference to the actual GitLab org release CLI and a link to the CLI tool. Any CI job with the release keyword is going to inject specific actions into your script that assume the release CLI is present. So if you're not using images, you're going to have to make sure the release CLI is built and available to your user on the host system when you run it, if you wish to use a workflow like this. The alternative is you kind of have to write the interactions yourself, either using like curl like type commands or like a GitLab Python package that I reference here as well. And then I've also included in the release job an example command for uploading a file, just with curl in this case, to the package registry that we've defined. Release job is a good example of when you use dependencies. So you make sure you're downloading the dependencies associated with this. So you're only downloading GCC, the artifacts generated in GCC build. And another helpful thing you should do here is if you're running a project and there's a lot of users, you can do something called protected tags, which is a GitLab server enforced mechanism, which is only specific users or maintainers can push tags to the repository that follow specific patterns. So what I've done in this example is I've limited who can push the tags that can trigger a release. And then you can obviously create the tag locally or use the GitLab GUI to generate the tag. The result, I should probably make this bigger. The result for all of this, is a release is generated. And it shows up in the GUI as, oh, I've released 0.1.0. It references a specific link to a Heat application that I've uploaded to GitLab, and that if a user has the ability to view the release, they're also able to download the binary that's built, and they have all the information they need. And you can expand this however you want. It gets a little complicated if you're managing releases of multiple applications or you're managing a release on an upstream repository. That's what we do with Jacamar. I don't build Jacamar in GitLab.com. I build it on like OLCF resources. And then I upload the resulting binaries and RPMs and SBOMs and all the details. It follows the same general flow, but instead I use this Python GitLab library and basically build the release that way and upload the packages that way as well. So it's an extra step because your CI/CD job token won't work correctly in this way, but there's some flexibility there if you're managing releases through GitLab. Finally, the container build. SPAC offers a SPAC containerize feature that allows you to convert a SPAC environment to like an actual container build. So if we take kind of our earlier SPAC environment and containerize it, we have an example Docker container or Docker file, or I guess container file, just generic, that handles the actual like build of in this example GNU plot at the version we need. So in that earlier plot job you ran that used GNU plot and created the PNG, it was built using SPAC a container file crafted with SPAC containerize, and this is the actual Docker file that you would run and build. It's just in this case our GitLab registry doesn't have the container registry like enabled, and that would not only that, it would take a ton of time to build all this and then upload it, more time than we have in here in the tutorial. So there's some features here and some examples of how you might choose to build on an HPC system. For example, using generating a local auth file in the podman example to handle authentication to your registry based upon environment variables like the CI registry user and the CI registry password that are provided to every CI/CD job. And some example rules to refine when you might choose to build this again, because it's time consuming, you might want to leverage rules based upon changes or environment variables to help um, save time in your job, not rebuilding something that doesn't need to be rebuilt every time. So let me stop there. I forgot to turn my camera on. Apologize. Um, and see if there's any questions. I kind of ran through those last two things just to kind of provide you an example. From a time perspective, I don't think we could go through them, but are there any questions from what we kind of covered there? There's something someone's interested in learning more about?
There's some good questions about the SPAC and using containers. Oh, I also don't have my camera. I think we got most of those sorted out, just curiosities about bind mounting and such. There was a good question Wooter asked, what's the difference between dependencies and needs when ordering GitLab jobs? I think we mostly answered it, but Paul, if you have any, my quick answer was that dependencies downloads artifacts from previous jobs and is really meant to be done between stages. And then needs, you can even do needs inside of a single stage to order jobs. But needs is really just a dependency ordering. It's not handling some of the automatic downloads of artifacts.
Yeah,
I
I
might
think
be wrong
any
somewhere there.
downloading artifacts, I think, is a side effect of needs more so than like the core component, which is that DAGs that it generates, and that out of order like job execution it enables.
Nice. Okay, yeah. So I'll start sharing my screen and jump in here and talk um, a little bit about I'll start here with parallel jobs briefly. We already ran through this example, which was great. The one bit that I wanted to highlight here that I meant to but ran out of time to add an example to the documentation is really just a little bit what Paul was talking about, where we're talking about a matrix here, but since we only have one condition, this would act, more like a vector or a list, where you could give a couple of different conditions here, and GitLab will go through each of those and run them in parallel. If you want to make this even more powerful, though, you can add more additions or more conditions. And so each list item here on the outside is you can make a list of conditions. So you could say, I want to test with a whole bunch of different versions of Python, for example, or a whole bunch of different compilers. Those could be your conditions on one side. And then maybe you have different versions of MPI as another condition. And doing that, GitLab will build the cross product of those two conditions. So it'll build every possible combination. And so this gets very powerful very quickly when you want to do something like compatibility testing with a system, or compatibility testing with different link or runtime dependencies somewhere, or maybe you want to change a couple of different optimization flags and a couple of different link flags, and you want to make sure that all of these different options work together. Matrices can make that very easy for you without you having to iterate. And the worst case scenario is you never want to have to like rewrite your job over and over and over again in one of these scripts, because the script gets immensely long and very hard to maintain. Instead, the matrix gives you a parameterized way to run through a bunch of different options. This can also be useful in unit testing, where maybe you want to test, for example, in the heat here, a whole bunch of different max t's, or a whole bunch of different random number combinations or something inside of there. So you want to do like an upper bound and a lower bound and a couple of different arguments. So that's really just my spiel on parallel jobs. I work with people making CI/CD scripts all the time, and I find matrices to be really cool and very helpful in making the scripts more easily understandable. You can even create a matrix of GitLab job tags, which I find really cool. So if you wanted to run, for example, at Livermore, instead of this being Jacamar, it would be the name of the cluster, typically, is how we have them defined. And so if you want to run your compatibility tests over a bunch of different clusters, for example, we used to have like Blue OS on something like Lassen or Sierra, the old IBM machines. maybe you want to test on an NVIDIA GPU and an AMD GPU, you could parameterize in one part of your matrix the different clusters to go run on, so that you can target it either NVIDIA or AMD or something. And then you can, instead of having a string here, you can actually have basically the variable, or you could call it like cluster, and then you would put in the variable cluster here. I use that in a number of different workflows, and it's amazing. So moving on from that, though, we're going to talk about scheduler actions, which is relatively new to Jacamar and is a really cool feature that Paul has been hacking on for, I think, came out truly maybe a little bit less than a year ago, has started to get integrated into more centers, and is now the default. So here, I'm gonna delete everything that we have in our GitLab CI YAML just to get back to a blank slate. So going back into our hello numerical world, opening the web IDE, and deleting everything out of here. And then we've got this first CI/CD workflow here, and it's got 3 stages and essentially 3 jobs that are all going to run sequentially. And this is somewhat the worst case scenario for HPC workloads, because by default, your GitLab is going to independently submit these jobs 3 times to the queue. So your first job will run, and at the end of your first job, the second job will be created, and GitLab will go and submit that second job to the HPC queue, and you'll end up back at the end of the queue. And then once that one gets all the way through the queue, it launches on a compute node, and then it runs. Then your third job gets rendered out by GitLab, gets submitted to the queue, ends up at the back of the queue, and has to get through the whole queue all the way again. So we'll go ahead and commit this as kind of an initial start so that we can get a baseline for seeing this go through our cluster here, and then just see how long it takes, see that it's submitting them all 3 times. I'm just going to call this scheduler actions and push this up. We'll go back over here. We've got our scheduler actions here. And you'll see that we've got these 3 jobs. They each depend on each other, which is what, when you say show dependencies here, you can see that 2 depends on 1, and then 3 depends on 2, which depends on 1. So clicking into here, we'll see they're really simple, right? You're just echoing a couple of things and waiting a few seconds. But we submitted batch job 49. And then after that gets through the queue, we start executing. And after which point, we start running a second job. Again, we submitted batch job 54. And you'll see as more and more of us are doing this on the cluster, it's going to slow down as the queue gets a little bit bigger. Scheduler actions are really cool in that they basically make this case a lot better by not having to submit to the queue multiple times. So with 2 simple additions, I'll let this get through the third job here, but I'll start talking about these 2 additions. So the 2 additions really are, first, we're going to request an allocation. So this is a new job. We're putting it in a special dot pre stage. This dot pre stage essentially always happens at the beginning of whatever pipeline that you're running. And this request allocation is using this environment variable called Jacamar scheduler action, where it's going to allocate 1 node and 1 core of a node. And it's actually not going to run anything in the script. So you can put anything in the script. Because of limitations with GitLab, you do have to have a script variable here, and you have to have something. So here I just put placeholder, and it's not a real command. It can be anything. There's a bit more of a example down here for some of that. So we will see this ran through all 3 of them. We're going to jump back into our web IDE. Here I'll add the request allocation, and I will pop that in here. Yeah, so I think Byron just asked, like, these dot stages, they're in the GitLab documentation, but they're kind of hidden. There's a dot pre and a dot post, and dot pre is always at the beginning, dot post is always at the end. And so for our purposes, it makes it really nice to bookend creating an allocation and then cleaning up the allocation at the end. So I've added the request allocation here. And then for each of our jobs, we're going to need to come in here and add the scheduler action to reattach to our existing allocation. So we create the allocation here. Now we will reattach to our allocation in the first job, the second job, and the third job. And so you can think of this as we're running, if you're familiar with Slurm, we're running salloc here to put in an allocation into the queue. And then instead of creating allocations for all three of these jobs, we're instead doing something like srun into our existing allocation so that we can keep a part of a node allocated and then bypass the queue entirely for our three jobs so that they run really as like one batch job on the HPC cluster, but you're running three individual CI/CD jobs here. So we'll reattach for all of those. And then here at the end, we want to be good stewards. We created this allocation. We want to clean up this allocation at the end so that it's not sitting around idling a node when we don't need it to. So we're going to create a new job in the special stage dot post, which just means it's always going to happen at the end. And there's a special rule in here. I talked about earlier, if you have an after script section and there's a timeout in after script, if you want to run a cleanup job later on, you can put this rule in here called when always. And when always says, even if some part of my previous, if job one, if job two, or job three, if they fail somewhere in the middle, I still want to run this. Like I always want to make sure that close allocation is run, no matter if these succeed or fail. And so that's really just saying for our purposes, we always want to cancel or clean up our allocation at the very end of our pipeline run. Again, our script isn't actually going to be run here, but because of a limitation on the GitLab side, we add a little placeholder. And now we should be good to go ahead and submit this as long as I haven't forgotten anything else. So we're allocating, we're reattaching in R3, and then we are canceling here. So I'm going to put in that we've added our scheduler actions. We'll commit this and jump back and watch our pipeline here. So we can see that dot pre always happening at the beginning in the dot pre stage. And this is going to go request an allocation. So we'll see schedule action, allocate. In the case that you're allocating something or you have an allocate job, do know that we're not going to run anything in script. We're not going to run anything in the before script here. These are just placeholders just so that you can be granted an allocation from Slurm. So good, we just had to wait in the queue once. We got through the queue, we got granted allocation 61, and we'll see now pretty quickly, our other jobs will start running and executing. And just by reattaching, they'll reuse that allocation. So you can see we echoed hello one and then we slept here. And we didn't have to get another allocation. We didn't have to wait the queue. So this will have moved on to our second job, third job, and then we'll close the allocation at the end. That's really all there is to it for scheduler actions. It's a really nice way to bundle a complex pipeline into a single Slurm allocation. You could think that you could allocate, maybe a full node or two nodes, and then you could pack a whole bunch of jobs into that allocation this way, where you have a whole bunch of tiny individual, whether they're unit tests or benchmarking was mentioned earlier in this. That's a good one or a good use case. So there we go. We got through our second and third jobs, and now we're cleaning up our allocation. So you'll see that we successfully cleaned up our allocation, and we're done. Yeah. So now I'll pause here just for a minute in case anyone had questions about scheduler actions or bundling jobs into a single Slurm allocation. Paul, correct me if I'm wrong, but I don't think scheduler actions works for Flux just yet, but it's something that we're adding soon. As I'm aware, it definitely works for Slurm, maybe not PBS yet. But
027 saw the addition of Flux scheduler
okay,
actions. So should
cool.
work
So
for
if
that answer. Yeah.
sweet, then that works for, I guess, both of the schedulers that we're using at Livermore right now. Um, and I think we're continuing to add on, especially if folks here have interest in any other ones like PBS. We can work on adding in the scheduler actions for each of those. I saw a chat message. Yes. So Wooter asked, essentially, you could allocate, for example, 3 cores here, and then um, if the first, second, and third job don't need each other, if you don't have this dependency, yes, they would run concurrently in that 3 core allocation. So if you know how many cores you need ahead of time, or a full node or something, yes, you can allocate basically for a parallel environment, and then as many of your jobs as are able to allocate in parallel will or able to run in parallel will run inside of that existing allocation.
Um,
Cool.
Eric asked a question. Does Jacamar use the tag or something else to figure out whether to generate Slurm or Flex commands? So that is determined by the runner configure. So when the runner and Jacamar CI are deployed, they're configured to target specific either the shell or Flux or Slurm executors. And at that point, that is what determines what Jacamar expects to interact with locally. So when the runner is registered, we encourage the individuals registering the runner to put tags associated with those executors, so it's easier to figure out which one you're targeting.
Yeah, exactly. And for the use case of Livermore, then we do tag all of our runners so that you could say a specific cluster and Flux on that cluster. Or I believe batch is also on there. If you target batch generally, and then if you did like a matrix of different clusters, you do run the risk of executing Slurm on one machine and Flux on another. But yeah, essentially in Livermore, if you go take a look at all of the configured runners, and you can do that, Paul showed this a little bit earlier, but when you're not my user, if you're in a Git repo and you want to see all of the runners that Git repo has access to, we can jump into the settings here, and you can jump into the CI/CD settings. You can click on this runners, and all of the runners that are made available for an instance will show up here, as well as all of their tags. So if you do this for a Livermore project, you'll see a bunch of different Livermore clusters, and then you'll see Slurm or shell runners or Flux runners. Yeah, so if you do a generic like a batch runner, um, yes, then each individual cluster based off of if it's configured with Flux or with Slurm, that's already configured into the runner on your behalf. It's not something you need to think about. And Jacamar will target the correct Flux or Slurm um, allocation system, and your job will just wake up in a batch allocation no matter what. Um, for the most part, the scheduler flags are pretty close between Flux and Slurm, but if you do need to modify them, specifically, I think for Livermore, I can't say about every place that has deployed Jacamar, but we do also give you the ability to say like, Slurm scheduler parameters and Flux scheduler parameters, and those will only be used or ignored dependent on the different scheduler that you wake up inside of. So you can define those more generically, run batch across a couple of different clusters, and then it will pick the correct allocations or banks or structure for a queue. So very cool. Thanks, Eric, for all the questions. I'm going to talk. This is a little bit more of a section that is less hands-on, is a good resource for people to come back to, but I'm just going to talk about working in large repos for a little bit. Large repos are kind of come with part of the territory of HPC computing, honestly. We have data sets that are really big. Um, Against the better interests of some people, sometimes part of those data sets end up in Git repositories as validation data for unit tests or something similar. Um, we also just have really complex codes, right? We're running 100,000 line or possibly million line giant simulation code bases at some level, or codes that have been around for a long time in HPC and thus have gotten a very large number of commits. SPAC has only really been around since 2015, but we're already up to, I think, like 40 or 50,000 commits in that repository. And so if you were to download the entire thing, it's about a quarter of a gigabyte. In that case, when you're running CI/CD workflows in an environment where you've got a large repository, a large portion of your execution time can just be downloading that repository over and over and over again. And so by default, Jacamar tries to help out with that by not downloading the repository over and over again, but instead keeping a copy of that repository and running git clean on it to kind of bring it back to a normal state, do a differential download of the last couple of commits, and bring you back into a good space. Um, However, this sometimes gets into contention with users typically have a very small home directory in HPC clustered environments. And because we're downloading files into this home.jacamar CI, folks can often run out of space in their home directory. And so I'll walk through, a couple of the ways that we can solve this. I don't know that any one way is a silver bullet, but dependent on the projects that you're working on or your specific setup at your HPC center, this is some advice to lower the pain of working with large repositories on shared file systems. And so the very first piece of advice that I'm going to give is that you can change the CI/CD job directory. You can do this two ways. Inside of your job, you can actually define a custom CI builds directory, and you can point this somewhere else. So you could point this at a Lustre file system if you wanted to download and have your project inside of that custom builds directory. Or you could point it at an NFS mount that might not be your home directory. For example, at Livermore, we have the workspace NFS clusters, and those are outside of your home directory. They don't have quite the same backup policies as your home directories, but we give people more space there. You can also, and I think this is something that oftentimes our code teams will do, um, inside of your home, that .jacamar CI directory, instead of setting this custom variable pointing at a different location, you can instead blanketly, you could move this directory out of your home directory to somewhere else, and then you could create a symlink that points, basically the location of the symlink is in your home under .jacamar-ci, and that symlink could point to some other location where you've moved to this directory where you have more space. Both of those will work. The custom builds directory is a bit more helpful if you have a project specific scope. So, for example, you've got a bunch of developers, they're all working on the same project. Um, you might want to centralize all your CI builds for that project into a single location so you could share artifacts or just manage the allocation on the file system a bit more easily that way. But if you're a single developer working on a number of different projects and your home directory is really tiny and you just want to blanketly move it out somewhere else, then I would probably recommend creating that symlink and pointing it at a different file system. And then Jacamar will follow the symlink when it gets set up, and it'll start writing up the files into that other file system, as long as that file system is available on all of the machines you would want to run on. The next piece of advice is that Jacamar, when you have a large directory, like I talked about before, Jacamar tries not to go download an entire repository over and over and over again. But if you're creating large assets inside of your repository, those get left after your job because your job could fail and you might want to go inspect those assets. And so typically I would say leave it so that the beginning of your job cleans up any previous Git repositories so that you can have a bit of an easier time going and debugging your code. Um, but if you've got a large number of these jobs running in parallel and they're eating up a large amount of file system space because you've got essentially like you're producing large artifacts in either your build or your unit tests or something, you can enable this variable called ff enable job cleanup. And this will instruct GitLab and Jacamar to clean up the repository after the job finishes instead of at the beginning of the next job start. Um, and this can substantially lower your disk utilization because basically you're always going to return to a clean state at the end of your job, um, which is just the minimal repository. It's going to delete all of those generated artifacts at the very end of your job. However, just be wary that you might have to turn this off at some point if you need to do some debugging, because on a failed job, it will still also delete um, the artifacts created, and you might want to go and inspect like a halfway built or something that got halfway through a build and air it out with a specific job log. In this case, it'll air out with that job log. If you don't save that job log as like an artifact back up to GitLab, um, it's going to go and clean it out of the shared file system. The next thing to talk about is git depth. And lots of folks are probably already familiar with this. You can use git depth when just doing a normal clone, right? So you can do git clone dash dash depth. Um, and oftentimes I recommend people do something like depth 2. If you do depth 1, it's going to delete the whole git history and essentially just download you like a tar archive and then unpack that archive of the repository state. That's great for getting, specifically just the files that currently exist, but you lose any of the history if you need to, for example, do like a git blame or something inside of your CI workflow. So I often recommend, like by default, GitLab downloads the last 50 commits of a repository on every push, or it will maintain a repository of 50 commits. Um, I recommend people generally lower that to 2 unless you're really doing something um, more complex, or doing something complex, either inspecting the git history, or if you're using something like git merge trains. And those of you who know what that means, you know who you are. um, Git merge trains essentially allow you to gate merge requests as they come in, rerunning a different set of tests on them with whatever is latest been tested inside of the main branch. But for folks that aren't using that, I typically recommend set git depth as a variable to 2. This will lower the amount of space that Git is going to take up on the file system. And then this is what I was alluding to a little bit earlier, the Git strategy. By default, Git is, or by default, Jacamar is always going to use the fetch strategy. And fetch essentially downloads the repository once, and then on um, subsequent runs of your repository, it's going to just perform a git reset and then do a differential pull. So that's going to save a lot of bandwidth and compute time, arguably, as it's just like cleaning up the file system and then downloading a few extra commits rather than downloading the whole repository over and over again. However, if you're really, really stuck on space, if you enable git clone and enable the feature flag up here of ff enable job cleanup, that means that at the very end of your job, it will delete the entire repository rather than running git cleanup on it. And this means that you will, at the very end of your job, end up taking up no more space than when you started with your job. And so that is kind of the maximal, if you're really, really short on utilization space and you really don't care about preserving the state of any of the repositories on the file system, and your repository is maybe small enough or can be compressed in a way that you don't care about the bandwidth of it too much, then setting git strategy to clone can sometimes be better. Also, sometimes we have seen on some shared file systems, uh, the operation of performing git reset where you're resetting the Git repository back to a clean state, is more computationally intensive than just deleting the whole directory and then reinitializing it from Git. This doesn't happen that often, but it can happen if you're using a lot of submodules, creating many, many small files like we do often in SPAC, where every package in SPAC, of which there are 8,000 packages or greater than 8,000 packages, is a small Python.py file. Sometimes it's easier to just blanketly delete that directory off the shared file system, which is a single operation to an NFS server that says, hey, this and everything under it, that can be deleted. And now I'm going to go reclone the next couple of commits. Um, and Git doesn't have to do an inspection of all of those files to make sure that you haven't changed them. Sometimes that can be a little bit faster. So those are my couple of recommendations for working with large Git repositories. Feel free to go back and play with all of these variables with your project, see if any of them help speed up or if they end up slowing down your repository clones, and find a configuration that works for you. But that's a little bit of advice. I'll turn it back over to Paul to talk about additional jobs, such as kind of, we already talked releasing your application a little bit, but just the last bit of this tutorial, and then we'll wrap up and have a little bit of time extra for questions.
Thanks. So, like we already covered, I think we covered enough about the additional jobs. So I think we can kind of wrap it up here. Everything we covered are features you can realize either with the runners available to you now, or hopefully runners that might be easier to set up. You can see yesterday's tutorial for details on that. But the core to all this is the GitLab server and how they realize CI/CD and the rules around it and how they manage the creation of jobs and components they add to that. So if Jacamar takes a fairly light approach and it does not try to override GitLab features wherever possible. So it really just tries to be the mechanism, the conduit of GitLab generated script with all your content in it, and all your scripts and all your Git sources and artifacts, and how do we run that on HPC in a safe and repeatable manner. So it's all open source. It's on GitLab. Well, I should probably put the links in the docs, but I'll throw it in chat. So if you're interested or you have questions, feel free to throw up an issue there, or if you run into problems, be excited to hear about them and see if we can help. But yeah, hopefully this helps everybody. And if you have any questions, definitely reach out. Alec, did you have anything else you wanted to add? We're only have a few minutes left, so if there's any questions, we should take those too.
Yeah, not really. I'm just going through answering questions from folks. Wooter asked if there's any specific Jacamar variables that support like a local or scratch disk. I said not really, not in the way that he's probably imagining, but you can point, if you know that you're always going to have that local disk on all of the compute nodes or the login nodes that you're executing on, you could point your custom CI builds directory at that. Just know that in that case, you might run the risk of, like, if your batch nodes execute on different nodes throughout the pipeline and they're expecting to share some amount of state or something, you'll have to do that separately. But you could point that at scratch space or at like a RAM disk if you really need to not point at an NFS file system for some reason. Okay, yeah. So the context Buddha was saying was in the allocate example. Yeah, so you totally could, if you're using containers or something, you could do the Jacamar variables to bind mount in from the container into something like a temp or var storage space. But if you're not in a container, you can just point at other file paths. There's no isolation or sandboxing inherent to Jacamar that doesn't let you touch somewhere else on a file system or somewhere else on a temp directory that your user would have access to when normally running an HPC cluster. And yeah, one of the kind of nice benefits of using the scheduler, like allocate and then using the existing allocation, is that you could share some like temp directory space on a single node. Like if you allocate a single node and you know that node has like a scratch disk space, all of your jobs could use that scratch disk space and expect their dependency artifacts or something inside of that because you're always going to end up on the same node.